Hey guys, welcome to the video on question 8 for DS 4400's practice exam 2. In this video, we'll be going over this question which asks, given only one sample x0 with label y0 and w, where w and f of x are logistic regression, weight, and average error, what is fx0? So before we actually get into solving this problem, I want to build some intuitions on some of the mechanisms that are present here. So first, we can define our logistic regression average error as this equation, f of x, 1 over n, sum from I to n of the cross entropy between p of I and q of I. So one thing that's not super intuitive to me is why are we using cross entropy as our metric of error? And here, so I'm going to write out the equation for cross entropy real quick. So this is the expected amount of information you get from Q according to P, right? So this is 1 over all possible values of X, the sum going through values of X times P of X log 1 over Q of X. So we covered this a bunch, but this term right here is the information we get from X according to Q. And then this is just simply the probability of X in P. So one way to look at this is, well, cross entropy is just trying to, estimate how much these two distributions agree. And one example where that might be a little bit more concrete is, let's imagine Q of X is really small. So let's say, Q of X is like super, super small, is tiny. So if that is true, we know that, this log equation, this part right here, is going to be a really big value. So what if P of X is big? It's close to 1, right? So it's super near 1. Well, in that case, it seems that we're going to be summing, P of X doesn't really diminish the magnitude of the information. So we're going to be summing, basically adding this really big value to our accumulated sum. Well, conversely, what if P of X is super tiny? So in this case, these two are kind of in agreement that, X is very unlikely in both distributions. Well, in that case, this information value might be really big, but P of X really diminishes the full magnitude of that information. So in that case, instead of adding a really big value, we're going to be adding a, not so big value. So in that case, we can with this in mind, we can think of cross entropy as trying to determine how much these two distributions agree. And so a quick statement here, these two are Bernoulli distributions. And if you remember what a Bernoulli is, it's simply a PDF which takes in a event and a probability, and it outputs P if K is equal to 1. So this means a success occurred, and it outputs 1 minus P if a failure. So Bernoulli is a discrete distribution with two outcomes, either a success or a failure, and we parameterize it by the probability of a failure or a success. So in logistic regression, we have a bunch of samples and a bunch of labels. The labels tell us, the labels are either a 1 or a 0. In the case of that we saw in class with the tumor example, our samples are a bunch of images, and our labels are whether or not there's a tumor present or there's not a tumor present. So really, we can just look at our labels as a Bernoulli distribution and just look at the actual output of our our actual label values as a probability. We can treat y of I as the probability of a tumor. So if we get 0, this means that there's a 0% chance there's a tumor. And if we get a 1, say 1% chance, 100% chance there's a tumor. Right? And conversely, we can think the same thing about labels. So our model is going to learn to output y hat, where y hat is a sigmoid. This means a sigmoid function of wt x, where w is the learned parameter of our model and x is some sample. So if you guys remember, this is going to output some value that is in between 0 and 1, right? And that basically tells us how confident that this image, back to the tumor example, like has a tumor. So y hat is equal to p of tumor. So if we, thus, we know that p of not tumor is equal to 1 minus y hat. So that's some just important framing about our predictions and our targets. And that's also a good way to look at, I'm losing my control, at what this pi and qi are. Well, pi is really just either yi if our event is tumor, if if our image is an image of a tumor, or 1 minus yi if it's an image of not a tumor. And then similarly, q of I is equal to y hat if we predict a value, the tumor, else it's 1 minus y hat, tells us the probability that we think it's not a tumor. Sweet. So now let's rewrite our objective. I'll get rid of these. So to simplify our objective, we have f of x is equal to 1 over n, the sum from I to n of, so remember the Bernoulli remember the cross entropy, so we have sum of like event in B, where B is the Bernoulli, so this is 0 or 1, right? And this is P of E log of 1 over Q of E, right? And, write this again, we have 1 over n, sum I to n, and this is another sum. And just to, work this out, we have the probability of 0 log 1 over Q of 0 plus P of 1 log over 1 over Q of 1. So remember earlier we said 0 is the chance of failure, and since P represents the distribution of labels, we know that this is just 1 minus yi, right, the ith label. And we also said that we can do the same thing here, but with y hat. So this is 1 minus y hat of I. Same thing can be done here. This is the probability of a success, which is just simply yi. And this is also the chance that we predict the positive class. So let's rewrite this equation. 1 over n sum I to n 1 minus yi log 1 minus y hat. Oh, sorry. 1 over that plus yi log 1 over y hat of I. So since we know this y hat just really represents a sigmoid of wt xi, we can supplement that in there, and I'm just going to real quickly write out the equation of the sigmoid, so negative WTXI. So supplementing that in, we get f of x is equal to 1 over n sum from I to n log, this is going to be a big boy, 1 over 1 minus 1 over 1 plus e to the negative wt xi plus yi log, let's remember, so 1 over 1 plus e to the negative wt xi. So we went through all of this derivation in class, so I'm going to skip ahead. We end up with f of x is equal to 1 over n sum from I to n the log e of wtxi plus 1 minus yi xitw. Actually, to be consistent, but it is the same thing, wtxi. So that's our final objective. If you want to see the steps that go from here to here, I recommend looking at the lecture slides. But now that we have not our objective, but now that we have our logistic regression average error function, let's use it to solve this problem. So rewriting it again, 1 over n sum I to n of log, let's look back at it one more time, of e to the wtxi plus 1 minus y of I wtxi. So in this case, we only have one sample, so we can get rid of this sum, and xi just becomes x0, so f of x0. Actually, just to speed this up, we know that x0 tw is going to equal 0, 1, 0.52. And this out is 0 times 0.5 plus 1 times 2, which is equal to 2. So f of x0 is equal to the log of e to the 2 plus 1 minus 2, right? And that is our final answer.